Well, thanks, Don, for reading that, so I don't have to. I was going to do a little bit of an update on our activities as well, but for the sake of time, I'm just going to largely skip that. But I do want to mention that for the Great Lakes Water Quality Agreement, the Groundwater Annex, we were charged with putting out an update report on the state of groundwater science in the Great Lakes, and it is finally out. And so that if you're interested in reading that, you can download it off binational.net. And in that, we do mention PFAS, and so that leads into my talk today. This is a new area of research for us into the ultra-short chain PFAS, and it's in collaboration with my colleague Claire Robinson, and then our students Ariel, Chris, and Evan at Western University, and then my technicians Kayla and Pam. And parts of this have been funded by Ontario MECP, as well as NSERC, and then us as well. All right, so just a quick introduction to PFAS for those who don't know. So it's this large group of synthetic chemicals that were first developed in the 1930s. So that's PFOA and PFAS back then. And since then, there's been the development or creation of thousands more. And the thing that sort of groups these together is they're very resistant to natural degradation processes. And so they've been termed the forever chemicals. Unfortunately, many of these are also highly toxic, both to humans and also to aquatic and terrestrial life. And so as we learn more about this, what guidelines that do exist now have been sort of tending to decrease over the past few years. There's a broad use of PFAS in society today, lots of things that we use in our house, stuff we actually put on our bodies, as well as some specialized uses such as aqueous firefighting foam, which they use for fuel fires. And so it's probably not a surprise, given this broad use that we're finding over the past 2 decades, PFAS in groundwater pretty much everywhere we look, but in larger concentrations around firefighter training areas, military bases, and airports, so places that use the firefighting foams. All sorts of manufacturers use PFAS, so we're finding them there. And then they're getting into our waste streams as well. So wastewater effluent and biosolids, some of which then we put on our agricultural fields, unfortunately, and then also landfills. So my talk, though, today is focusing on the very tiniest of the PFAS, so the ultra-short chains. And so these ones consist of 1 to 3 carbon chains, and you can kind of see the molecule structures there. They tend to be highly polar, and thus we expect them to be quite mobile in groundwater systems. And so for a PFAS plume, you might expect them to be at the edge, the far edge of the plume, traveling faster than the larger PFAS. They're largely breakdown products of the PFAS, the larger PFAS that we're developing, but can also be, byproducts, also breakdown products of the larger PFAS. And one in particular I just want to mention is TFA, so trifluoroacetic acid. And this is a degradation product of HFCs and HCFCs, so gases that we've used to replace CFCs. So they're up in the atmosphere, which means that TFA is being created and raining down upon us. So in our lab, we've developed analytical capabilities to analyze 4 of these ultra-short chain PFAS. They're listed here. And then also PFBA, which has 4 carbons, and so technically it's a short chain. But we'll include it because we can get it. So why are we interested? First off, there's not much known about ultra-short chain PFAS compared to many of the other PFAS, especially in groundwater systems. And so we don't really know how much is out there, what sort of concentrations to expect, and what are all the sources. It is, as I mentioned, a toxicity issue, so for drinking water wells, but from Environment Canada standpoint, we're concerned with the aquatic ecosystems that would be receiving groundwater discharge from that's been contaminated with PFAS. In addition, there's the potential to use them as groundwater tracers for PFAS sources, or generally using it sort of as this early warning for the groundwater pathway for other PFAS to come. And finally, from a practical standpoint, for our lab, it's great because we can analyze these on the same run as we do our artificial sweeteners. So we kind of get a double bang for our buck. Okay, so this is, like I said, sort of a new area for us, a newly developed tool in our toolkit. And so our initial foray, we just decided to piggyback on some existing projects. So one is into historic landfills, where we're looking to see if leachate contaminated groundwater is moving out and reaching surface water bodies, and then also septic system inputs to streams. So quite similar, looking to see if we're getting wastewater components moving with groundwater into streams. And so from the ultra-short chain perspective here, very simple, we just want to see if we're finding them associated with either the landfill impacted waters or the septic impacted waters, thus indicating these as potential sources of these ultra-short PFAS and these being routes for their movement into the environment. Okay, so I'll just start off with a little bit about from the landfill study. This will be data from 2023, and this was Ariel's project. We've got 2024 data that's still being processed, so we'll add to this. So for this work, we collected samples from 40 historic landfills across southern Ontario, and we broke this data into 3 types of sample sets. So streams, where we measured upstream and then downstream as it passed the landfill. Drains, we're just calling little streams that formed actually on the landfill site, and then any groundwater seeps that we found popping out along these streams. And for this study, we used ammonium and our artificial sweetener saccharin as our indicators that there's a landfill impact on that water, but also using the sweetener acesulfame to determine, well, maybe that's from wastewater, because it can contribute those as well. But there isn't the acesulfame in the landfill leachate. And so from this first set of data, we found that 20 of the 51 samples were deemed possibly or likely impacted by the landfill leachate. And so a likely example is this little streamlet or drain that's starting out right here. So here I'm just showing the ultra-short chain PFAS data. I've broken it down. So at the top in pink is TFA, because it has much higher concentrations. And then at the bottom, I've lumped the rest of them together in the purple. I've also separated out the drains and the seeps, because those were interested in the concentration compared to the streams, where we're doing the concentration change. So downstream minus upstream, to see what's been added along the way. And so for all of these box plots, what we're doing is comparing the samples that were deemed not affected by the landfill to those that are grouped and deemed likely or possibly affected. And so with the drains and seeps, I think you can clearly see there's a difference, higher concentrations for the samples that are impacted. And so this is an indication that the landfill or the leachate impacted groundwater is also contributing these ultra-short chains, so a source there. In comparison for the streams, though, we didn't see significant differences between the two sets, and it could just be that with these larger volume, the streams here, that we're just not able to pick up the signal. Okay, so that was just a snippet from the landfill. Now just a snippet from the septic systems. So for this study, we're using the artificial sweeteners acesulfame and sucralose as our indicators for septic effluent input. And so for one part of the study, this was Evan's work. He collected samples from 46 outlet streams from 46 subwatersheds across southern Ontario. And we did not find any relationship there between the ultra-short chain PFAS and the sweeteners. We think part of this might be due to the fact that the ultra-short chains tend to be at fairly low concentrations relative to the high concentrations of sweeteners that we find in septic effluent itself, in addition to other sources of ultra-short chain PFAS, including the atmosphere. So we were thinking we got some high background in some of these. So sort of strike one on that one. But for the second one, this is Chris's project. We're having a bit more of a field scale approach where he was looking at longitudinal sampling along a stream stretch or collecting from a stream through a rain event. And so taking a more detailed look at it, maybe some indication of an influence there. And I'll just show one example. This is for a rain event that happened for a small stream that passes through a little hamlet called Brownsville in Ontario. So the hamlet's all on septic systems. And so for this rain event, you can see there's kind of a two-parter with a little bit of rain first and then a larger rain event a little bit later. And on the big graph then I'm showing all the concentrations sort of before and through this double rain event. So looking first just at the artificial sweeteners, so that's orange and red triangles. I think you can see that the concentrations go down after the initial rain event and then rebound. And then after the second rain event, we see that again, this down and rebound. So to us, this is indicating that the sweeteners representing the septic systems are coming through a slower pathway, likely groundwater related, and then they're being diluted as the runoff is coming in with the rain events. In contrast, if we look at the E. coli, which is in the green diamonds, you can see that the concentrations actually increase after both parts of the rain event. And so this makes sense. It means the E. coli is probably coming in with runoff, probably from the nearby agricultural fields around the town, maybe even from the streets as well. So a clear difference there. Now when we look at the ultra-short chain PFAS, 3 of them here in blue circles, we do see an initial increase after that first little rain event. So that may be that it's coming in with some runoff source, which was a little bit unexpected, or perhaps it's actually coming in with the rain. So we haven't figured that part out yet. But then we do get this sort of dilution pattern, and then through the second rain event, especially with the TFA, you can see just the dilution pattern, not an increase, kind of more following the sweetener pattern than the E. coli pattern. And so maybe, this is just one set of data yet, maybe an indication that some of the ultra-short chains are coming in with the septic effluent, with the sweeteners. So short and sweet, take-home message. Just want to let you know that we are detecting some ultra-short chain PFAS in southern Ontario waters, with indications of a groundwater input from landfills and possibly septic systems, but with more data to come on that. And with that, I'll thank you for your interest.